Okay, lesson 85. We got some theorems to talk about today. That's the short of it. Okay? Some of them are kind of review, some are kind of new. Excuse me. Okay, so first one up here, maximum and minimum value existence theorem. This is a review of an old theorem. If f is continuous on the closed interval I, which is defined as a to b, then f attains a maximum value, capital M, and a minimum value, lowercase m, on interval I. So all that's saying is if you have a graph that's continuous, you draw it. No matter what you draw, there is a max somewhere and there is a min somewhere. Which, part of me wants to say that's common sense. You draw something, there has to be a max and a min. Okay, so that's just maximum minimum value existence theorem. It just says that a max and a min exist on a continuous closed interval.
So if it were like a y equals a number, would the max and the min be the same then? Or does that not apply to this? I was just kind of curious.
What do you just ask me?
So if it's like a y equals, so it's like a straight horizontal, would the max and min be the same, or would this not apply to the theorem?
It's a valid question. Because that would be continuous on an interval. But by definition, can max and min be the same? I don't know if they can or not. If we're going to say this theorem applies to all functions, and that's a function, then I would say that it means the max and min would have to be the same. But that, I'm not sure that you can define max and min to be the same value. Maybe you can. I don't know. I don't have a clear-cut answer, sorry. It's good food for thought. Okay. Intermediate value theorem. If f is continuous on the closed interval a to b, and n is a number between f of a and f of b, then there's at least one number c between a and b, inclusive for which f of c equals n.
I think we do this one already.
I believe so.
Very familiar.
Yes, I was just thinking, I believe we did do intermediate value theorem. Okay? Because the old ones here are the maximum minimum value existence theorem and then intermediate value. The new one is the mean value theorem. Okay? So, I drew a picture at the time. Should I try and draw the picture again and see if... Because I am 99% sure we've done this, unless I'm just, So, f is continuous on the closed interval from a to b. Let's see if I can...
Hi, Aubrey.
Hello, Aubrey.
There you go. There's your hello, Aubrey. Okay. So, if f is continuous on a closed interval, a to b. So that means there is some graph drawn between a and b. Okay? Can you tell that's a and b? Not really. But I promise they're a and b there. Okay, so if f is continuous on the closed interval a to b, n is a number between f of a and f of b. So what you have to realize here is that f of a is going to be the y output when x is a. F of b is going to be the y output when x is b. Okay, the idea, n is a number between f of a and f of b. My graph is too small. So n is a number between there. Then there is at least one number c between a and b. I don't know where this is exactly going to end up. Okay. There's at least one number c between a and b, inclusive, for which f of c equals n. Okay, so c is between a and b, and it has an output that is between f of a and f of b. That's our intermediate value theorem. I don't know, does that sound a little familiar?
Yeah.
Okay. I mean, if I put it in words, your input of C is between the inputs of A and B. Your output of N is between the outputs of f of A and f of B, which is what f of C is. Okay? So, and that's just, now that's dependent on the graph has to be continuous. Okay? So that's our intermediate value there. That intermediate value exists there. Okay, one we're going to spend most of our time talking about today, mean value theorem. If the function f is continuous, that's going to be a key word, right? If the function f is continuous on the closed interval a to b and is differentiable on the open interval a to b, so just where the endpoints aren't included, then there exists at least one number c in the interval a to b such that f prime of c is f of b minus f of a over b minus a. Okay. Notice it uses the word exist in here. When it uses the words exist, realize that this is an existence theorem. This is just saying that if these, what's the word I'm looking for? If these criteria all come together, then this situation exists. Okay, so this is an existence theorem. So the function, in order for it to be true, the function has to be continuous, has to be differentiable, and if that's the case, there'll be a number, basically where the derivative at that number is equal to f of b minus f of a over b minus a. I tend to think of this as slope. Okay? I tend to think of this as slope. That's what, I think of it as. Now, the best thing I can suggest is let's look at some examples to make it make sense. Is that okay? So if we look at example 1, demonstrate an understanding, that's what I'm going to help you grab here, of the mean value theorem by applying it to the function f of x equals x squared minus 2x minus 8 on the interval negative 2 to 1. Okay, so I underlined two key words in the mean value theorem that we have to verify before we can even continue. The first word was continuous. I can only continue with this problem if f of x is continuous. Okay, so I can't even look at this, I can't even consider this problem if we determine f of x is not continuous. So, what do you notice? Look at f of x. Bless you. Okay.
There's nothing in the denominator.
Okay. F of x, what is this graph?
Parabola.
X squared minus 2x minus 8, it's a parabola of some sort, yes? So is a parabola continuous? Yeah, it's a continuous graph. There's no option, no issues there. So it's continuous. That's the first thing. It's just kind of a mental check. Okay? On an open-ended AP situation, you would have to possibly state it if you're trying to apply mean value theorem. The next question. Is it differentiable? So can I take the derivative of this graph at all points on the interval negative 2 to 1? Because that's the thing. This only all matters on negative 2 to 1. What if we talked about when is a graph not differentiable? Or when is a function not differentiable?
When there's a hard point.
Okay, when there's a hard or sharp point. Yes? What do you know about a parabola? It's a curve. Are there any hard or sharp points? No. So, and just based on the fact that it's the interval negative 2 to 1, I don't know exactly which portion of this parabola mine is, but I know it's some basic part of a parabola that would be okay. So is it differentiable? It is. I'm going to even write under here, no sharp points, because that is your easiest indicator. Okay, if we're going to demonstrate an understanding of the meaning, first of all, where are my A and B values? I like Wade's answer. What do you guys, does that make sense to you? A and B, we said A is -2 and B is 1. Because how's the theorem work? It says on the interval A to B. And what did they give me? An interval A to B. Now, if we're looking at our mean value theorem right here, f prime of C equals f of B minus f of A over B minus A. Here I've got A and B, yes. I also need to have f of A and f of B. How do I find f of A and f of B? Plug it in, yes. So if my A is -2, that means I'm going to need to know f of -2. If B is 1, I'm going to need to know 1. What do I get when I plug -2 in?
You're going to get 0.
Because -2 squared is 4, -2 times -2 is 4, 4 plus 4 is 8, -8 is 0. What do I get when I plug in 1? 1 minus 2 is -1, minus 8 is -9. Okay, so the idea is f prime of C is what we're trying to figure out. How do we find f prime of C? F of B minus f of A. So I'm going to start off saying, I agree, I'm going to start off saying f of 1 minus f of -2, which, yes, I agree, as Jack said, is going to be -9 minus 0 over.
1 plus 2.
Okay. It's going to be B minus A, so 1, I'm going to say minus -2, but we know 1 minus -2 is going to be 1 plus 2. What do I end up with here? Yeah. -9 over 3, which does end up to be -3. Okay. We just found that f prime of C equals -3. Which, keep in mind, we basically did y minus y over x minus x, right? Which means we basically did a slope. Okay, I mean, it's not technically slope here, but on the flip side, it is. So what we found, we don't know the value right now, but at some value of C on this interval, there is a derivative, officially it's a derivative, of -3. Now, let's go with let's look at the other side of this real quick. If f of x is this given function, what's f prime of x?
2x minus 2.
You guys okay with the 2x minus 2?
So the -1/2.
So, if we're talking f prime of C, if I'm going to call this f prime of C instead of f of x, I'm just going to put it in terms of C. But then, yes. So, 2c minus 2. What did we just find f prime of C is equal to?
-3.
Yeah, so f prime of C, I need to set it equal to -3. So 2c minus 2 equals -3. Do the math. Add 2. -3 plus 2 is -1. Divide by 2, and we have -1/2. Okay. All of that to show that at some point on the interval -2 to 1, we had a derivative of -3. At what point did we find that to be? At the point -1/2. So let's see, where am I going to write this? Kind of didn't leave myself the room I needed to. For some value, C, which in this case equaled -1/2, the derivative or if you prefer the word slope, I'll put that in parentheses, is -3. And this is according to the mean value theorem. Yeah, I should have left a little bit more room there for myself.
What is after the slope? Because I see something -3. Is that okay?
Is.
It is. Okay, sorry. I thought it was a symbol.
Oh, what?
A symbol.
It is. I thought it was a symbol for some reason. I wasn't saying her name.
I was like, I know that's not what that means.
Sorry, my handwriting does get kind of sloppy, especially when I'm trying to squish it in sometimes. It's hard to kind of see.
I wish my notes were that kind of sloppy. Your sloppy compared to my sloppy is not the same.
Agreed.
Yes.
All of your notes manage to be like super neat all the time. And then I look at mine and I'm like, was I awake when I wrote these?
I'm also looking at how I've already previously set up when I've worked it on my own, or like at this point I just grab past notes and set it up like that so that I, can plan ahead, because otherwise I would be running out of room a lot more than what I do. Okay, so.
Is that a 1/x²?
On the next problem, I think it is. Yes. I have it written in darker. Okay. The value of the function f of x equals, and that does say 1/x² minus 1 equals 0 at x equals -1 and x equals 1. The line connecting the point -1, 0 and 1, 0 is horizontal. So the slope of the line is 0. Determine whether the mean value theorem can be applied to prove the existence of a point between x values of -1 and 1, for which the slope of the tangent line to the graph of the function, or in other words, value of the derivative, equals 0. Okay. So we're given a function up here, right? F of x equals 1/x² minus 1 equals 0 at x equals -1 and x equals 1. The line connecting the point -1, 0 and 1, 0 is horizontal. Okay. Can the mean value theorem be applied to prove the existence of this point between x values of -1 and 1?
What does it say is continuous? So if there be a hole, I think you put it as 0.
Okay, so the first thing we do need to question, is this continuous? It doesn't say it's continuous, which I'll be honest, they're probably not gonna tell you specifically if it's continuous or not if they give you the equation. You're gonna have to figure out, is this continuous or not based on the equation.
It's not continuous.
Yeah. Now, what interval are we looking at here?
That's right over the break.
Yeah. Your interval is -1 to 1. So the idea is any value we plug in between -1 and 1 needs to work. The one you guys are, I started to say the one you guys are zeroing in on.
Oh.
I wasn't even trying to. Okay. So the one you guys are picking out, which is the key, is x equals 0. Because what happens when we put in 0? You're putting 0 in a denominator. Can we put 0 in a denominator?
No.
No, you can't have 0 in a denominator. So x cannot equal 0. So what did that just do to the continuity of this graph?
There is.
It's not continuous. So you don't even go any farther because the graph is not continuous at x equals 0. Thus, the mean value theorem cannot be applied. And that's essentially what I'm going to write.
And that's it for this problem?
Yep. We are stuck because it's not continuous. So mean value theorem only works if you can justify it's continuous and differentiable. Graph is not continuous at x equals 0. Thus, mean value theorem cannot be used. Okay.
That one's my favorite.
Your favorite? It's nice when you can see those and catch those things. I mean, that's what it comes down to. So, okay, example 3. Demonstrate an understanding of the mean value theorem by applying it to the function f of x equals x to the 2/3 on the interval -8, 27.
That should be square root.
So the first thing Jack is over here talking about is, what are we asking ourselves? Is this graph continuous?
I think it's continuous, but I don't think it's differential.
Okay, so let's talk about continuous for a moment. Continuous, we can plug in all values between -8 and 27. Remember, what does 2/3 do?
Squares and then cube. Takes the cube.
Okay, so you're squaring and cube rooting, right? They don't have to be whole numbers, but you can cube root anything, right? Positive or negative. If we're square rooting, we'd have a different story. But you can square root any number, and cube root any number, and thus you can square any number. Is 0 okay?
That's my mistake.
Yes.
You can cube root 0 is 0. You can square 0 and get 0. Okay, so we can rationalize that continuous, we're good. Next question.
It's not differential at 0.
So yeah, the next question becomes, is it differentiable? Jack, you're questioning 0. Why are you questioning 0?
Well, it's somewhat like the square root graphs where it has that, but it's on both sides.
Mm-hmm.
And that would come to a hard point.
Okay, so when we have, do you guys remember what the cube root of x looks like? This is how I always teach this graph.
It's kind of like a longer square.
Well, if we just look, at the cube root of x minus the squaring. The cube root of x is x cubed but turned sideways, right? So this is a cube root of x. But this isn't the graph I'm talking about, okay? Now, what happens when we square this is everything has to become positive. So this part's already positive. What happens to this part?
Positive.
It becomes positive, which means now it's going up here. So it's still continuous, but what did I just create?
Sure.
A sharp point. Okay, so thus it is not going to be differentiable. Okay. Another thing is when you take the derivative of that, you end up with x in the denominator. And x in the denominator does not allow a 0 in the denominator. Okay, so I'm going to say we found a sharp point. And again, the graph ends up being something like that. And we have a sharp point. So, mean value theorem cannot be used. And keep in mind, mean value theorem cannot be used specifically where? On this interval, right? We cannot guarantee a value of C on the given interval. Does that mean that C couldn't exist at all? No, there could be something outside of the interval, but we just can't guarantee it on the given interval. So we cannot guarantee a value of C on the given interval. Trying to think. Tempted. Okay. I say I was half tempted to go ahead and find that value. I was debating just as a practice, but you guys have the other one as a practice, don't you?
That looks like it was
Algebra 2. Speaking of which, I have yours for you guys today. I'll talk about it later. Test is actually going to be Tuesday.
Wait a minute. That's not what we
Review day is Monday. Lesson 87 is your next lesson in your notes, and that is shell method, which I don't teach anymore because I discovered that it's not part of the AB curriculum, and it just complicates the whole washer and disk method. And if shell method's not part of the curriculum, you know, like I used to teach it, it is. It just complicates the washer and disk method. And so I quit teaching it a couple of years ago. So I guess I have zero plans to teach it.
Oh, does point circumference and multiply by height?
Possibly. I don't even remember at this exact moment.
It's 2 pi r.
6 days or less.
Yes, you only have 3 lessons. And I had mentioned previously you guys would only have 3 lessons between tests. And so, you know, and I'd said next week, I know it's last week in the 9 weeks, you'll have a test one way or the other. Whether it be 2, you know, so. Huh? It'll be the last test in the grade book. So.
Will the tithing thing be interrupting like all thing of lessons, or will we have like a review day afterwards?
Are you talking about math day?
That's what I know. Yeah. I just didn't know how that would interrupt.
Let me get back to you on that one when I mean, honestly, we won't do anything that day. I can't remember where it's going to fall. Well, I've had to bump a day since I originally did my planning. So I can't 100% say without until I look at my plan book where it's going to fall, and how it will work out. So it'll probably just be, we just won't do anything that day. It'll be like a missed day.
That's next week.
No. Okay. Are we ready for example 4 yet? Maybe. The function f of x equals the absolute value of x minus 1 is equal to 0 at x equals negative 1 and x equals 1. Does the mean value theorem imply that f prime of c equals 0 for some number c between negative 1 and 1?
I'm gonna go.
I was just waiting for you guys to. Okay, so the first question. Can we confirm continuity?
Yeah. That's an absolute.
What's this graph look like? Absolute value down 1. So absolute value is what? V down 1. So is it continuous?
Yeah.
Yes.
Well, that's not different.
But why is it not differentiable?
It's a hard point 0.
Okay. It has that hard point at 0. So it's not differentiable because there is a sharp point at x equals 0. And this is because we specifically had to look at the interval negative 1 to 1, didn't we? Okay. And the idea is when you take the derivative of absolute value of x, I don't know if you remember or not, but there's an x in the denominator. So when you plug in 0 into that derivative denominator, it doesn't work. So I'm going to say mean value theorem does not apply. Okay. We've got a Rolle's theorem to talk about.
I'm still filling in example 4. So how do you write so much faster? I look down for a second with that whole line written out.
It's like Cassidy yesterday. She looked away for a second and came back and said, what?
Yeah, I'm really confused, but I figured it out.
You can't look away for a second. There's just not time in
It
calculus.
really was. It was I was picking up a light thread. I turned around and you just have everything written down. And I was like, wait.
Okay. Rolle's theorem. 1, f is a continuous function on the interval a to b. Okay, so if f is continuous. 2, f of a and f of b equals 0. So the function equals 0 at these 2 points. And I'll provide a picture here in a moment. And 3, f is differentiable on this interval. Then some number c exists between the points a and b such that the derivative equals 0. Okay, you got that idea? Let me give you a visual to help. So I'm using this line here as my x-axis, okay? And on this x-axis there is an A, and there is a B. Got it? There's an A and a B. So first of all, I have to draw f so it's continuous. And then also, f of A and f of B both equal 0, which means the graph at A is on the x-axis. The graph at B is on the x-axis. There's some continuous graph that connects these. I just draw a curvy shape here. Okay? It's saying that some number C exists between A and B such that the derivative equals 0. What is derivative in our brains? Derivative is slope. So, where do we have a slope of 0 on this graph? Slope of 0, right there, at that tippy top point, at that max, what happens when I draw the tangent line? Because remember, derivative is slope of the tangent line. Well, my tangent line to a max is a horizontal line. And we could have just reversed this graph and made it upside down, and then it'd be a minimum. But as long as you remember, derivative is equal to slope of the tangent line. Right there, where is point C? Point C is where my max is happening. Or if this graph was upside down, point C would be where my minimum is happening. Okay? So my graph was continuous. Yes, I drew a continuous graph. I drew a differentiable graph. No sharp points. I drew a graph that f of A and f of B are both equal to 0. So if this is my x-axis, and I plug A and B and I get 0. All those things are true, so some number C exists in between A and B where the derivative equals 0. It's kind of another way of saying that there will be a min or a max in between those points. That's what we're saying. But we're saying it in the terms that the derivative equals 0. Does that make a little sense now? With the picture? I'll be honest, it doesn't make sense to me until I have the picture. Like, I need the visual of these type things for it to really cooperate. Okay. Suppose two stations are 60 miles apart, and we drive, and the drive between the two is exactly 1 hour. Then, the average speed of the trip is defined as following. Average speed, f of 1 minus f of 0 over 1 minus 0. Or in other words, 60 miles per hour. Think about it. Does that make sense to you? Two stations are 60 miles apart. So at time 0, you're in your 0 location. Does that make sense to say? In time 0, you're at location 0. You drive an hour, so at time 1 hour, how far have you driven? 60 miles, right? So the idea of, based on our mean value theorem earlier, f of 1 minus f of 0 over 1 minus 0. That's going to be 60 minus 0 over 1 minus 0. Okay? So that's the idea that we can use with the mean value theorem. And I think I just explained some of what is written down below, I just realized. Forgot to keep reading. So this is the mean value theorem. It says that f prime of c, the derivative, is f, what it says up there. So at some instance c in the interval, they had to be going 60 miles an hour. Okay? Which, think about it, makes sense. If it's 60 miles to get somewhere and you do it in exactly an hour, you have to be going at some point at least 60 miles an hour, right? Technically, if you want to get there, you don't always go exactly 60. If you sometimes go below 60, you're also sometimes going to have to go above 60, right? Okay. So now, if the posted speed limit was 55 miles per hour, then at some point the driver was going in excess of the speed limit, 60 miles per hour, or going in excess of the speed limit. I'm tongue-tying myself horribly. I don't know have I made sense of this? Okay. If you get the average value to be, or based on the mean value theorem, to be 60, you had to have been going 60. If the speed limit was only 55, we had to have been speeding. Because technically, 60 is speeding in a 55. Technically. I'm not saying we all agree. I'm not saying we all abide by that. I'm not saying any of us abide by it, but I'm just saying technicality here, yes? If you want to argue 56 is speeding in a 55, right? Yeah. Okay, so notice what it says. This can be useful in courtrooms. The speed limit on a highway is 65 miles per hour. At 6 p.m., a police officer sees a truck go by at 60 miles per hour. That officer radios another police officer 70 miles down the highway who sees the same truck go by at 7 p.m. traveling at 60 miles an hour. Find the average speed of the truck between 6 p.m. and 7 p.m.
Are they really trying to get this guy or what?
Well, yeah, obviously. Okay, so,
This is the other 65. I thought he hit his brakes when he saw the police officers.
he was going 60 at that point. So let's look at how long it took him to get to point B.
I know, but why would you radio him just to say that one guy's going 5 miles?
Makes you look suspicious. I don't know. I mean, hello, you think the cops don't see us when we hit our brakes as we pull into their range? I mean,
Never.
That's why I just
As
said
everyone
that
goes from
cruise
10
is
miles
like
an hour.
Actually,
down
they
to
do.
that little
They
bit
can
of
see the
the
headlights back on.
exactly. That's, I mean,
When you're on the gas, the headlights are.
Yep. Okay. So, average speed of the truck between 6 and 7. I mean, we can think about our formula up there.
You traveled 70 miles in 60 minutes, so it had to be on over 60 miles.
What was his distance? How far did he travel? They were 70 miles apart, yes? So he went 70 miles. And what was my time? 1 hour. So he at some point had to have been going, yeah. Because if he
totally hit his brakes when he saw the cop.
well, yeah.
Well, no.
Yeah, I definitely.
I usually set my cruise track to everywhere I go. That way I can just do not hit it down so it doesn't show your brake lights.
I said, just as long as you're not going incredibly over, the smarter thing to do is just to take your foot off the accelerator, not hit the brakes. But
There could be somebody behind
yeah.
you.
So, okay. So, the truck driver is ticketed for speeding, but he argues that he was never clocked at 60 miles per hour. That should say above 60 miles per hour. Considering the speed limit is 60, right? He's not going to be ticketed for going 60 and a 60. Okay. The truck driver is convicted by a judge who points out that he must have been traveling 70 miles per hour at least once. Is the judge right? Whether we want to admit it or not, right? Okay.
I never thought about that.
Interesting thought, isn't it? You can be going 60 here, and say he was going 60 at the end also.
Yeah.
Yeah, you could be going 60 and 60, but if you're going 60 and 60, then you could have only possibly traveled 60 miles in an hour.
Well, you never know. He could have,
I think that's the wind push him
yeah.
and help
And he
him.
would pushing, he'd be going over 70 miles per hour.
Anyways, I'm going to say yes, and I'm going to write down some explanation.
Or maybe he almost had a red light, so he had to hurry up and accelerate through the intersection before it turned because there
10
was somebody
miles per
behind
hour
him.
more.
Yeah.
Oh, you don't even know how fast you're gonna go sometimes.
Yeah, really. You really gotta punch it sometimes.
Okay, if he never went over 65 miles per hour, then he could not have traveled how far in that 1 hour?
70 miles. You can only go 60.
He could have only traveled 65 miles in that hour, right? So yeah. So I'm going to say then he could not have traveled more than 65 miles. Not have traveled more than 65 miles in the hour.
Sometimes you get to a yellow light and there's somebody too close behind you to step on your brakes. So it's like, and you don't know if they'll be able to slam on yours. You just gotta accelerate through.
I'm going to throw in the calc lingo. By mean value theorem. The driver's speed reached at least 70, or reached 70 at least once. I mean, technically, you and I, well, I guess it could have been one sustained time, but you and I know it was not just for a second that they,
As a truck, he's also supposed to go 500.
It doesn't say what kind of truck it is though.
Yeah, this could be a semi.
But I drive a truck when I drive my husband's truck.
Yes.
You know. Anyways, yeah. By mean value theorem, the driver's speed
I like them.
reached 70 miles per hour at least once.
People are always we're forcing them to go to different lanes. And it's really hard to drive a big old truck like this. I feel bad for them.
Have you driven one?
No. But my dad knows a lot of people who are truck drivers.
But you don't know them?
I'm like, I was really